Okay, I think we should start now. Hello, everyone. Thank you very much for attending today's webinar. And my name is Tao Feng. And today I'm going to talk about one of our recently published RFI, Point of Use Water Purification. I have my email address on the title page. So if you have any questions about this RFI after the webinar, please feel free to email me. We also encourage our inventors to use our pre-submission feature on our Xinova network. So we will be able to provide feedbacks for your preliminary ideas. Shivani, can we turn to the next page? Great, thanks. Oh, okay. So as always, we have muted all the audience in order to lower the background noise. If you have any questions during this webinar or at the end of the webinar during the Q&A session, please use the Skype chat box to submit your questions. If you are a computer user, the chat box is located at the bottom left corner on your computer screen. If you are a mobile user, the chat box is on the upper right corner of your mobile screen. Okay, Shivani, next slide, please. Great. So before going into the technical challenges of this RFI, let's take some time first to talk about the problem definition. What exactly is the point of use water purification? So on the spectrum of water purification systems, one end is the point of entry purification, which is used by government entities to purify water from the environment before introducing the water to the municipal systems. The most effective point of entry purification systems all use the technology based on the principle of reverse osmosis. In addition to the municipal facilities, the beverage production facilities also have the on-site reverse osmosis system. So that's how we got our bottled water or bottled beverages. The reverse osmosis system is an industry standard because of its effectiveness, but it also has the drawbacks of being very expensive and bulky. It also generates large wastewater streams. So on the opposite end of this spectrum is the point of use water purification, which is utilized by the end consumers, for example, at the tap or in the field. Point-of-use purification systems are far smaller and less expensive as compared to point-of-entry purification systems. However, most of the point-of-use purification systems only improve a few characteristics of the water. And in this RFI, we don't care about point-of-entry applications. We only care about point-of-use water purification applications. And the primary application where we will use the water purification technologies is the on-site beverage production. For example, the soda fountains in the cafeteria setting. Well, the output water produced by conventional point-of-use purification technologies is perfectly acceptable for residential consumption. It is not as pure as is necessary for standardized beverage production. So you will see that the soda fountain application actually has its own challenges. That will take us to the next slide. We will talk about the challenges of this RFI. Shivani, can we turn to the next slide? Okay, yeah, probably my internet is a little bit slow here. So sometimes if you have turned, I just see it coming. Great, thanks. So in this slide, you see a picture of a soda fountain that we are all very familiar with. I don't know whether you have the experience of some odd-tasting soda at some soda fountain, even though it's the same brand of soda that you have been drinking all the time. One main reason is that these on-site beverage production systems, they can have widely different water sources. Also, they probably will use different water purification systems as well. Poor quality water can have a significant effect on the taste and the smell of the fountain beverages. What's more, the water can also affect the performance of the fountain system. For example, the balance of water to syrup ratio and the quality of the carbonation process. In fountain beverages, they are more than 80% of water. But the fountains, not like the beverage production facilities, they don't have the benefit of a reverse osmosis water purification system on site with pre-filters and tightly controlled output specifications. As a result, the water used in these soda fountains may not taste as good as the bottled water. So the challenge of this RFI is to find water purification technologies that are specifically designed for the point of use applications, such as soda fountains. The ultimate goal is to produce pure water with consistent taste, but without using the more expensive and bulky reverse osmosis system. Similar to residential applications, soda fountain application, the water filters cannot be too large and too expensive. That's obvious. But the soda fountain actually has a unique requirement for the water flow rate. The water filter system's flow rate for soda fountains should meet the combined flow requirements of all the carbonators. So for this RFI, we're looking for purification technologies with flow rate not lower than 2.5 gallon per minute. So 2.5 gallon per minute. This is a very important requirement, and we're going to talk more about this flow rate requirement as well as some other important requirements for this RFI. Shivani, next slide, please. Great, thanks. So first of all, let's quickly take a look at some common contaminants that will affect the taste, the color, and the safety of the water. First, chlorine or chloramine, which is a mixture of chlorine and ammonia. They are commonly used in water treatment facilities. They oxidize and break down organic molecules of sugars in the water. And these reactions will produce many different compounds that can negatively affect the taste of the beverage. And also because free chlorine is a gas, it will gas off along with the carbonation after the drink is produced. So creating this swimming pool smell that we're all very familiar with. And another odor of the water is this rotten egg smell. This is because of the hydrogen sulfide in the water, and it is produced by bacteria. We're also very familiar with this kind of smell. And iron and other metals, they can give the water a bitter and metallic taste, and this is certainly not desirable. And salt contaminants, such as carbonates or sulfates of calcium and magnesium, they will crystallize along the walls of pipes, forming this we refer to as a scale. And we all know that equipment maintenance or replacement due to the scale buildup is significantly expensive sometimes. And lastly, contaminants such as bacteria, lead, and mercury, they will not only affect the water taste, they are also very serious health concerns. And in addition to these individual classes of contaminants, when evaluating the water quality, especially for the soda fountain application, there is another important specification which is called total dissolved solids, TDS. The TDS measures the combined content of inorganic and a small amount of organic substances in the water. And common inorganic dissolved solids include cations such as calcium, magnesium, potassium, and sodium, and anions such as carbonates, nitrates, bicarbonates, chlorides, and sulfates. So these are all very common dissolved solids in our drinking water. Even though the TDS concentration is actually not a health hazard, but ionic contaminants still can affect this taste of the water negatively, and which can be very off-putting for the consumers. In addition, excess minerals in the water can promote the scale buildup, as I have just mentioned, and which will result in large maintenance costs. And other concerns about the TDS level for soda fountain application include it will reduce the carbonation in the fountain beverage actually. It can also cause the ice machine associated to the soda fountain to produce fast melting, cloudy, or soft ice. So these are all very important concerns for soda fountain application. Therefore, this total dissolved solids reduction is actually one of another top priorities for this R5, as long as this flow rate requirement. We are looking for technologies that can reduce the TDS level in the water to less than 10 milligram per liter. Shivani, next slide. Thank you. So in the next few slides, I'm going to briefly introduce some commonly used water purification technologies and their strengths and weaknesses in terms of the water purification performance. And first of all, even though this reverse osmosis system is not the target of this R5, RO system usually used in the point of entry applications. I'm still going to talk about it so you will understand why reverse osmosis technology is not suitable for the POU applications. Reverse osmosis uses a semi-permeable membrane to remove ions, molecules, and large particles from drinking water. The water is collected after permeation of this membrane is purified product stream, while the retained fluid contains a high concentration of contaminants in the reject stream. And this reject stream, the amount of this reject stream actually can be rather large. So industrial reverse osmosis system usually is designed in a sequential multi-membrane, multi-stage configuration, in which each membrane in the series is only making a small contribution towards the overall water recovery. And the picture shown on the right-hand side of this slide illustrates a three-staged industrial reverse osmosis system. You probably can imagine such a multi-staged RO system is way too large for point of use applications. And in addition to the size, the industrial RO system is also very expensive. Even though we currently have some inexpensive and smaller sized residential RO units, but the data shows that those inexpensive and smaller RO systems can only harvest 20% of the total water used, which means we're sending 80% water to drain or waste. This is certainly not desirable. In addition to the large waste stream problem, the flow rate can be another concern. Using a commercial product as an example, the flow rate of a commercially available under-counter size RO unit is only 0.37 gallon per minute. This is much smaller than the 2.5 gallon per minute requirements for this R5. So we can see that this reverse osmosis system has many drawbacks. It's not suitable for the purpose of this R5, that's for sure. Next slide, please, Shirani. Other than the reverse osmosis technology, here is a list of some other common water purification technologies. And you will see that neither of technologies on this list is perfect. It has, each of them has its own weaknesses. So I'm going to talk about these technologies in the next few slides. Shivani, can we turn to the next slide? Thank you. So first, the filtration. Filtration is a very common water purification method. Most basic filters are simple porous materials that exclude large particles and bacteria. More complex filters can include additional materials. For example, silver nanoparticles, which can kill bacteria or mold trapped in the system. The figure in this slide is a multi-stage filtration unit from U.S. Water Systems, which has 4 stages, with each stage targeting one or more contaminants that the other stages are not capable of addressing. So this 4-stage cartridge is very effective to produce pure water, but the total dissolved solid level that it can achieve still cannot meet the requirements of the present R5. Another issue is this unit uses polyphosphate to deal with the scale problem. The last stage of this unit is a slow-release polyphosphate cartridge, which can separate hardness particles to prevent them from precipitating and forming deposits. But for this R5, we prefer not to use polyphosphate because of the increasing environmental concern towards the disposal of phosphorus-based chemicals. There's a current trend using greener technology, some chemical-free agents to deal with this scale problem. In addition to this polyphosphate issue, the flow rate about this unit is okay, but still on the lower range of the requirements of this R5. This 4-stage cartridge, the flow rate is about 2 gallons per minute. I think it's acceptable, but it's on the lower range. So this is a filtration, and this is a commercially available example for filtration. And next we will be talking about activated carbon. Activated carbon we're all very familiar with. It's a porous carbon material, which is ideal for non-specific absorption process. Activated carbon is very commonly used in all kinds of water purification applications, but it's actually not powerful in terms of removing metal ions, especially lead. It also has very low or even no absorption affinity for salts. That will be a concern for the soda fountain application because too much salt in the water can cause a lot of problems. So the picture in this slide shows a commercial carbon filtration unit from the company Selecto. This unit combines a titanium oxide fiberglass membrane with a hollow carbon filter. And it was mentioning that this patented hollow carbon water filtration unit, it actually offers very high flow rate. And from the company's website, it says selective filters allow users to reduce chlorine, chloramine, scale, bad taste, odor, and particles of the size from 0.5 to 1 micron at the highest NSF listed flow rates available in the market, 5 gallons per minute to 10 gallons per minute. I think this is very impressive, the 10 gallons per minute flow rate. But the issue is this unit cannot reduce the total dissolved solids to the level required by this R5. So this is the activated carbon. And the next slide is ion exchange. Ion exchange, which is also called deionization, uses charged resin to bind ions of the opposite charge from the water. So this is often performed on water to remove calcium and magnesium ions in the process known as softening the water. The ion exchange process does not remove organics or biological threads, which means it can only be utilized as a later stage unit in a multi-unit process. The resin also must be regenerated or replaced after a certain amount of time of operation, making it the process less attractive for continued use. And another issue is the cost. Current ion exchange units are too costly to provide feasible solutions to the present R5. Flow rate for ion exchange unit is also a problem. Using a commercial example from Pure Aqua, an ion exchange cartridge of the size of 12 centimeter by 50 centimeter, the flow rate can only go as high as 1.25 gallons per minute. This is definitely much lower than the 2.5 gallons per minute, the requirement for this R5. So next is disinfection. The disinfection is a process to kill a significant percentage of pathogenic organisms, and it's usually the final stage in the water treatment process. The primary use for disinfection include ozone, ultraviolet radiation, and chlorine. But this disinfection process addresses only the reduction in biological contaminants, so they're not sufficient for the purpose of this RFI on its own. The flow rate for disinfection process is not an issue. An example is a commercial UV system. The flow rate is in the range of 8 to 20 gallons per minute. So the flow rate is okay here. And lastly, is distillation. So this is a very conventional purification method to separate water from its contaminants with different boiling and dew points. Distillation is very effective, but it has to deal with the concentrated waste stream, similar to reverse osmosis. And it is very slow due to the phase change of the bulk water. So it's not really good for point-of-use applications. In addition, the distillation requires the input of significant amount of energy because of the large heat capacity of water, making it less efficient than other methods for the point-of-use applications. The flow rate specification for distillation, I found an example of a vapor compression distiller. The flow rate is only about 0.17 gallon per minute. I think this is even slower than the reverse osmosis. So apparently distillation definitely is not something we're looking for this RFI. Next slide. I think we have looked at all these currently available technologies, and we can summarize them in this table. In the first row of the table, I listed this ideal situation. So ideal solution we're looking for in this RFI should produce zero water waste with high flow rate, and it cannot be very expensive. And the water quality has to be very good. But this is the ideal situation. And in the next few rows that follow are the realities. We have looked at all these technologies, and each of them has its weaknesses. Neither of them is perfect. For example, the single-stage filters, the water quality is not ideal. And the multi-stage filters, they are okay, but the TDS, the total dissolved solids level, does not fulfill the goal of this RFI. Reverse osmosis system and distillation share some common drawbacks. The large waste stream and very slow. Ion exchange and disinfection, they only address certain type of contaminants, so they're not good on their own. And activated carbon filters, they are cheap and they're good, but still the TDS reduction requirement is not good for the activated carbon. So neither of them is good for the purpose of this RFI. So that take us to the next slide, the invention suggestion slide. What exactly we're looking for in this RFI. And here is the list of the ideal units, the list of the features for the ideal unit. It should be a single cartridge system with high flow rates, minimum water waste, and high total dissolved solid reduction. So again, these are three important specs and top three priorities for this RFI: the flow rate, waste stream, and TDS reduction. If your invention is very good in either of these three specs, and we probably can compensate some other performances of the purification technologies. And also in this slide is the list of the water quality requirements. Again, these are all ideal situations. It's probably too aspirational to ask a single invention to meet all these requirements. But these are still very important numbers. So please remember these numbers when you're working on your ideas. We probably won't accept inventions or solutions that deviate too much from these numbers. in the next slide, we have some additional consideration for commercialization. So in terms of the cost, we're looking for something less than $500. And in terms of the size, we're looking for some product dimensions which can fit in a soda fountain machine or under a kitchen counter, which means this cannot be very large. And to be more specific, the upper limit of the unit size is 92 by 61 by 61 centimeter. And lastly, the flow rate. Again, this is a very important commercial consideration. You probably can imagine in a business restaurant or a sport complex setting, a soda fountain with slow dispensing rates would be disastrous. So again, we're looking for technologies that with a flow rate larger than 2.5 gallon per minute. Again, these are also very important consideration. Please remember them when you are working on your ideas. And the last slide is out of scope. This is very simple. We're not looking for anything that improves the current reverse osmosis system. This is very simple. So before going into the Q&A session, here's the broadcasting for our next webinar. On June 26th, we will be talking about trade secrets. Because Xinova, sometimes in some cases, we will protect our inventions or solutions we found from our network with trade secrets as opposed to patents. So we want to talk about the trade secrets. We want to help our inventors to understand better this type of the IP protection tool, trade secrets. Okay, so that's all I plan to cover in today's webinar. Thank you again for your time. Now please submit your questions using the Skype chat box. Okay, I see some questions. What is the first question? What is the limit of the amount of wastewater generated by the system? We don't really have a hard number on it. So the less the better. We're not asking absolutely zero wastewater, but again, must be minimum. And I know some inventors have some questions about this, but sorry, we don't have a hard number on the limit. So the less the better. So that's my answer. So the second question is, why are we targeting the total dissolved solid less than 10? Is it safe to demineralize water? This is a requirement from the sponsor of this RFI. So we didn't invent this number. I think the reason is the total dissolved solids level is very important for the soda fountain machines. It does not only affect the water quality, so does not only affect the beverage quality. It also has some negative influence on the ice machine and on the carbonation process. So the total dissolved solid level is quite important. I believe that's the reason why we require it to be very low. We have another question. What is the cost of current soda fountain purification unit? I don't know exactly the cost, but I know currently we are using very simple carbon filtration cartridge. So some manufacturers include 3M, Selecto, and Pentair. I would imagine those filtration units are not very expensive. They are just simple carbon filtration units. Primarily, they remove chlorine, odor, and sediment. So definitely not very expensive units. if you are interested in the specific price number, I will look it up and email to you. Another question. One way I was thinking to increase the flow rate of the filtered water was to be a bit out of the box and just get the water that is filtered into a storage container, first of some kind. Is that permissible? Could we essentially store an appropriate amount of the filtered water either inside the soda fountain or in the restaurant itself? I think this is definitely not a crazy idea. I believe this type of holding tank idea has been in use currently, but I doubt that can solve the problem, the flow rates to the level that required by this R5. But holding tank is definitely okay to compensate slower flow rate. But we still hope that the technology is not too slow. But the holding tank is definitely can be a secondary method to help the flow rate issue in the solution, I believe. Another question, any guideline for cost per gallon during its use life, including energy minus? Cost per gallon, I don't think we have in the R5, but I remember I have seen it somewhere in the reference material. Let me check. Sorry, Zhihong, I don't have this number on top of my head. I will have to double check the number and back to you. And I'll email you the number. I definitely have seen it somewhere. You're welcome. That's perfect. I think we can get the flow rate pretty fast internally, but once filtered, the comment from the inventor asking about the holding tank, right? Let me double check. Yes. Alex has another comment. I think we can get the flow rate pretty fast internally, but once filtered, it seems like a buffer of stored water might be the best bet. Thanks so much for your response. Okay, say hi to Edward. I will if I meet him. Okay, can you email this number to us all? I believe this was referring to the cost per gallon, right? Okay, I will. This is related to the cost per gallon. Okay, yes, I guess. Actually, I'm still looking for that number. I definitely have seen it somewhere, just couldn't get it now. Do we have any other questions? Seems there's no questions coming in. I guess then we will close today's webinar. If you have any more questions, just email me. And also, if you have any idea using the pre-submission features. Oh, I see another one. Could a waste stream be biologically recycled? Could a waste stream be biologically? I'm afraid I don't quite understand. Okay, be biologically recycled. Okay. That will definitely help. I think from one of the conversations we have with the sponsor of this R5, we believe the sponsor of this R5 said that some kind of recycling is acceptable as long as it's not too costly and it's cannot be very difficult to implement. But and also the amount of the waste stream cannot be too large, even though it can be biologically recycled. Still remember, we're talking about the soda fountains in a restaurant or in a cafeteria. So on-site recycling probably is not quite easy to implement. So keep that in mind. But if you have a recycled waste stream, it's definitely help, I think. Okay. Do you have any more questions? Okay, then I think I'll be closing the webinar. And thank you again very much for attending. And we hope to see you next time.